Yeah, thank you for the opportunity to speak and to talk about even numbers. I'm going to start by talking about something that's slightly more sophisticated than even numbers, but just a very basic case of what math we talked about. So let's let L be a p-adic number field. Doing an integer is well, so it's perfectly fine and interesting to restrict essentially to p-adic integers, and then L would be obtained from p-adic integers and the p, so we take the p-adic rations. And very classical invariant is the so-called Galois homology or tau homology of L. And this is the continuous group homology of its absolute Galois group. And that group can act on representations as C P take twisted by one, which will be a fancy name for mu p, and maybe I could twist this by an arbitrary weight and take the W tensor power of mu t. All right. There's a theorem about Galois homology in this context. It goes back to 8. So canonical isomorphism is Galois homology, the second Galois homology of Zeeman P, which is implemented by the Hahn invariant. And regardless of how that isomorphism is defined, the key point is that this composite right, take the tensor product of these two homology groups, then I can subtract top product, and then the Galois homology of just one. And just said that was Zeeman P. And claim that this is a perfect thing. Okay, so this is the basic theorem that I would like to try to generalize here. Let's do this. Let me just be very concrete and give an example. So if I look at direct sum, these homology groups, keep the this is easy to describe as an FP module. It's a free vector space over FP adjoining V1 plus minus this graded field on generators. Right, so let me just draw a little picture of that. So if I want to draw all of the Galois homology groups with all the Tate twists, I'll have some specified elements here. This is at the prime 3. And then I'll also have all of the V1 power multiples of these elements, and I will also be able to multiply by V1 inverse. So this bottom line here is the 0th Galois homology, and the only thing in the 0th Galois homology would be powers of V1 that I'm suppressing. So here I've just drawn unit, but there's also V1 times the unit and V1 inverse times the unit. And let me just say that this key group is one-dimensional FP vector space, as was already declared over there. The name of its generator is this class V1 inverse partial lambda 1. So V1 inverse times this class over here. I want to come back to this example later, but let me just say that all of this is related to algebraic K theory. Yeah. So our lambda one is what 100. So I will perhaps at some point describe a way of calculating this group, which will make these names meaningful. But for now, I'm just saying that this is a name for some vector space generators. So I'm just giving arbitrary names to.
This is just the vector space generator this, right? These are just symbols. These here.
These are just what? Sorry.
Symbols, like symbols.
Yes, they're just symbols. They may acquire meaning later, but for now they're just symbols. I just wanted to indicate very concretely that you can just calculate these things, and also you can see a kind of rotational symmetry here. So I hope it's believable that this is a point radiality group, right? This is the state duality I wanted to highlight, the fact that you can take two elements and multiply them, and every element pairs with a unique other element to get you V1 inverse partial lambda 1. So this is what I want to view as the dualism class in the top homology. The way it's drawn, maybe you would think partial lambda 1 is what I would think of as a dualism class, but this is the one that Tate wrote about. Okay. So what is the relationship with algebraic K theory? So it turns out, as it's described just an hour or two ago, that direct sum of these kinds of cohomology groups have something to do with the motivic filtration on algebraic K theory. So explicitly, these things are the homotopy groups of the associated gradient, the motivic filtration mod P in the name group V1. So K theory is a spectrum. I can mod out by P and invert V1. And that process of inverting V1 was alluded to in the previous talk. It is the process of a tau localization, as it turns out. Well, let's not go into why. But this is just a formal thing I can do. I can take this motivically filtered thing, look at its associated gradient, mod P invert V1, and I get exactly the sum of these Galois group. So another way of expressing this theorem of Tate is to say that this expression satisfies a kind of point radiality. Okay. And then by work of ownership, so you may or may not know more about. I don't know if it's going to be from this point of view, but there is also motivic filtration on topological cyclic homology, not just on K theory. And as I continue throughout the week, I will remind you of what topological cyclic homology is in its relation to K theory. But just for this introduction here, let me say that there's a motivic filtration on TC of the ring of integers. Okay, and so it turns out that if I take the associated graded of this, mod P and V1, I get the same thing as if I get a QIC. So for the point of view of understanding Galois homology, I could view it as having something to do with a Galois group and representations in group cohomology, or I could view it as having something to do with algebraic K theory of this field L and some motivic filtration element, or I could use this theory of topological cyclic homology, which again I will eventually remind you of. And from this point of view of topological cyclic homology, I'd be interested in the filtration on the ring of integers rather than the field itself. But you get the same expression here, which is just the direct sum of these Galois groups. Okay.
Sorry, maybe I don't know much about it. So technology, is there any version with coefficient? I mean, here it looks like that you have multiple coefficients, but do you have any version for?
Yes, so this is with coefficients, these twists of Yuki, and we will talk about very general notion of coefficients if we get to it in a little bit. Okay, and then so I'll look at the example again of ZP. To look at the motivic filtration on TC of ZP, you can mod out by P. And they said that if I invert V1, then I get this direct sum of the Galois cohomology groups. Which I've drawn a picture of, and which is a module of this on FP adjoining V1 plus minus. So indeed, V1 is inverted. You can see the V1 acting on the scale of homology. And I want to just mention that if this is some kind of version of this before inverting V1, it contains perhaps strictly more information than this étale theory. And in fact, we can explicitly write down these groups phi. These are FP adjoint V1. That's exactly the same generators that I wrote here, except now we're a module over FP adjoint V1, but we haven't inverted V1 yet. Oh, this is a calculation one can do. It was done by Boxted and Matson at odd primes and by Logness of prime 2. And this thing is I'll highlight the bond. I want to say a little bit about what that means. So if I look at the elements in this Galois homology, I can divide them into two kinds. There are the ones that are in the image of this map, and there are ones that are not in the image of this map. So the things in the image of the map are those that I've named here, and the ones not in the image would be things in that whose names involve multiplication by a negative power of v1. And what do I mean by this Lagrangian statement? I mean that if I look at anything in the image of this map, its Poincare dual is not in the image of this map. So for example, the unit has this Poincare dual whose name involves the v1 inverse. And anything that is not in the image of this map has Poincare dual that is in the image of this map. So there's a sense in which this thing sitting inside here is the extra information of a Lagrangian in this self-dual homology. Another remark is that there's another thing that is kind of maybe naturally in this picture before inverting V1, is that I also have an invert V1 map on the K theory of this field as opposed to the topological cyclic homology of the ring of integers. It's the same self-dual target. And this is also a Lagrangian. And this is indeed something that was already discussed. This is so maybe if I put a third slide, it's clearer. So we said that before tau localizing, before inverting V1, this is obtained from this object by some kind of truncation that was discussed in the previous talk. And that truncation is defining in a sort of very simple way a Lagrangian. So there's two Lagrangians that naturally fit inside here, but they're not the same Lagrangian. And maybe there's some interest in that. I will not go into very much about measuring the difference between these Lagrangians. But maybe one remark we want to eventually go into is that Hahn and Murray produced a generalization of this picture. So they produced Lagrangians in the Galois homology arbitrary crystalline representations. So there was a question, why am I only taking coefficients in these particular representations? And in fact, I don't have to prove that there's a kind of duality for Galois homology for many kinds of representations. And there's a notion of crystalline representation. And for those, there is, according to Hahn and Murray, a canonical Lagrangian coming from this crystalline structure somehow.
One question.
Yeah.
So this Lagrangian statement is true for any L? Or
Yes,
is it,
for any of these p-adic number fields. Yes.
What's the next to find about today?
Oh, Gerst, or I just wanted to, there's a motivic filtration in the pictures, but these motivic filtrations collapse in these cases. So there's not much going on with those filtrations. It's just if you want this to also be bi-graded, you probably need to include the motivic grade. Okay, and the way they do this is using the theory of so-called prismatic F gauges, whatever that means. So part of what I hope to do is talk in more detail about this theory of topological cyclic homology, and highly associated to that theory is this theory of prismatic F gauges, whatever that is. Okay, so right. So as a homotopy theorist, might ask myself why I got into this mess. And the answer is largely motivated by some calculations of the SUNY roundness. The SUNY roundness calculated the times is 5. You could look at this topological cyclic homology of AU. So here I mean topological complex K theory, P completed. And so again, topological cyclic homology is some theory which we'll discuss, but it's something that you can apply not just to discrete rings or schemes, but also to ring spectra, things like topological complex K theory. And I would like to generalize a lot of this theory to handle arbitrary ring spectra and not restrict attention to discrete rings. So what did these guys, assuming anonymous, notice in the 2000s? They observed that if I invert V1, and if I invert V2 now, this is the inclusion of a Lagrangian into a self-dual, multi-dual, FP of 1 V2 plus minus logically. So it certainly seems as though there's something to be said about the fact that this is self-dual, about the fact that this is Lagrangian, which directly generalizes the story in the discrete ring case. Furthermore, the conjecture is compatible with analytic filtration.
Sorry, one question. I know you'll get into the names of things later, but like the V1 over there, a priori is really just like a parameter that shows up, but these are like chromatic V1s or VIs, right?
I mean, this V1 is also a chromatic V1, and that would be, as we get into defining the motivic filtration and topological cyclic homology and stuff, it will be apparent that these are the chromatic V1s.
So is that FP inverted V2 really like more of a K theory, or is it just a?
It's the homotopy groups of Morales K theory.
Right.
I wouldn't say that it is arising as Morales K theory.
Oh, okay.
What are our goals? Next days, I hope to first of all explain why this is true. This means some package of the self-duality statements and the Lagrangian statement, not just for the topological cyclic homology. L or the also other things, DMF, there's many different rings, and I want to give some kind of general reason why this duality in the Lagrangian matrix, something that sort of explains a large class of rings that behave like the ring of integers in the number field. And another thing I would get, so I want to do this, maybe this by a kind of direct, maybe you could even say computational argument. Just went with sum of runs. But also, I guess we're in Europe, so I'm supposed to view all Poincare duality statements as consequences of 6 functor formalisms. Maybe I can flee to America later, but in Rome or Copenhagen, whatever. We're going to want to define category. Let's take this kind of crystalline representations, whatever that means, or this nice ring spectrum. And these categories, they serve as coefficients for whatever kind of Galois homology theory would be in the picture. So categories of coefficients. But again, when we get into this category will be easiest to define and easiest to understand when we're dealing with nice ring spectrums. When nice here means something like regular, maybe even if you like this word quasi-syntonic, some kind of condition sort of analogous to the smoothness condition that appeared in the previous section. And if you really want to understand things from a 6 functor point of view, you may also want some kind of category of coefficients even for not so nice ring spectra. And so then we will begin, depending on time, to explain how to handle arbitrary ring spectra. The tool here would be sort of notion of maybe calling it synthetic rings. These are the equivalents to Hahn by 1 spectra given the beautiful results of Hahn weapons and Berkeley here. So if we get to discussing arbitrary ring spectra and synthetic E-infinity rings, the point will be to, inspired by this work, give a kind of treatment of norm spectra that does not logically rely on any of this work and has a somewhat different flavor, perhaps, from these approaches. Okay, let's see, how much time do we have?
Half an hour more Boolean.
Well, norm spectra are due to Bachmann-Poirot, but the relationship between this algebra geometric theory, norm spectra, and the theory I'm going to propose is mediated by these words. Yeah. Okay, so maybe before really digging into this, I should say something about TC. Ecological technology built on THH. All of its associated expressions. So there's some theory, which is a little bit complicated, called topological cyclic homology. And we're going to want to understand it together with the motivic filtration on it. But what it is some kind of construction that can be built from a much simpler construction, namely THH, as long as we remember from extra structure present on THH. THH has a circle action, it has a Frobenius, it itself has a motivic filtration. And before discussing all that structure on THH that gets us TC, maybe we should just first think a little bit about THH. So let's use the definition. T is in one. Let me see a tilted field. It's this result somewhat familiar with the product. Not so terrifying to define. And our goal eventually will be to prove that this tensor product has a lot of extra structure, including again a circle action of Frobenius and motivic filtration. But then he also mentioned that it can this B bimodule can form relative to B coefficient in that bimodule. So there's a notion of THH with coefficients, and it's just given by this expression B tensor B off. And what does it mean to be a bimodule? A bimodule is nothing more or less than a B tensor B off module, which allows us to find this expression. So there's some fundamental computations that maybe are good to keep in mind. Your mileage may vary, but I would like to throw up some concrete computations that exhibit some of the phenomena that we're talking about. Like some famous examples. Yes, there in the box said, just the limit up here to PHA to the P. We went with that's FP adjoining the 0. The degree of mu 0 is 2. So the topological Hahn homology of FP is a polynomial on a degree 2 generator. If you don't know this result, I'm not sure how much this is going to help, but you're suggested to go look up some YouTube videos by Thomas Nicholas and very wonderful resource for getting into this stuff. I also mentioned topological homology of the p-adics, which is our key example of one of those rings of integers. And though the THH of the p-adics is mildly complicated, you get something simpler when you take coefficients in FP. So there's a ring map from ZP to FP that makes FP a bi-module, so I can form this THH with coefficients construction. And the homotopy I get FP of the one and stereo of the one. And if you agree with me on is the key, and if you agree lambda on okay, I'm going to throw up one more example. DHL coefficients of FP. Here, L is the atom summand. You complete the I star L is ZP everyone. It's a version of connective topological K theory, which has a generator in degree 2p minus 2 instead of in degree 2. So K theory has a hot element in degree 2, but it has this summand, which is also a ring, which is just the ZP adjoining the p minus first power of hot element. And this is.
By being E1 on infinity and E0.
I mean, these are all the infinity.
Okay.
We can talk about that you actually need to run some of these arguments, so perhaps let's not focus on that. There's plenty of interesting things to say about the infinity rings. And I just throw this up here because it's an example of one of these ring spectra that's not a ring. So you can't rely on some of these theories that are based in algebraic geometry. You have to somehow do something else to understand what's happening here. But if this is an unfamiliar object to you, it's already interesting to focus on say, these top two cases. So there's very similarly, here mu2 is in degree of 2p squared, and the Hahn is still in degree of 2p minus 1. So these are some computations which maybe you know what to do, or maybe you can learn how to do it. We can do something in the papers of Nicholas Carlson or Foxted or Sean Levy and David Lee wrote a paper that includes this L case in a nice way. That's a very baby example. Right, I want to just make an observation. For any of these rings, DHH, P of coefficient of P, becomes non-collinearity algebra. On either converting you or killing you. So if I take one of these rings and I kill this polynomial generator mu, I'm left with an exterior algebra, the most basic example of a non-collinearity algebra. But also, if I invert mu, I'm left with an exterior algebra now no longer over FP, but rather over the graded field FP again in the plus minus. In either case, we get a point regularity algebra. Furthermore, map. And THH into this thing where I invert mu plus the thing where I pin mu. This is the Lagrangian. So what does it mean to say that that map is Lagrangian? Well, let's call this map alpha. So this is just the direct sum of the natural map into the localization in the quotient. Well, I can write down this as dual again, they're both Poincare duality algebras, so they're identified with their dual, and then I can look at the dual of this alpha map and turn that to the dual of THH. And the claim is that this is a co-fiber sequence. The co-fiber sequence. And that's what I mean by this map alpha being Lagrangian inside this Poincare duality algebra, just the direct sum of two smaller Poincare duality algebra. This means that alpha composed with the dual of alpha is null, and actually this composite is a co-fiber sequence.
Could you just quickly recall what Poincare duality algebra is? Or
Well, I just mean that there's a canonical identification of this thing with its dual. In this case, it's the statement that if you take, say, an exterior algebra, everything has you can multiply with the unique thing to get to the top class, which is this product of the exterior generators.
So on the level of quantum groups, this is fine. But on the level of spectra, but we just need the usual symmetric model.
So this means the linear dual, but part of what we will discuss is, I guess, how to. I mean, this, if you like, is a map from the tensor product of this thing with itself to the Anderson dualizing spectrum. I think if you want to say it spectrally, that's what we should say. Yeah.
Which dualizing class do you have in mind for one reason?
I think that I have in mind the lambda 1 and lambda 2 and not meaning what's not. But I have in mind which other one makes this theorem shapes.
What do we call this Lagrangian? Does that have something to do with like imitating half-dimensional submanifolds?
Yeah, it has something to do with how Poincare duality interacts with the inclusion of Lagrangian into a bigger manifold. Maybe I'll write something about that on the day.
One more question. So the first thing is already self Poincare dual, and the second thing was not, but there's a map to it still. And it is.
These are dual,
Okay.
and this is just a map. And then we take the dual. Okay, so why am I putting all this down? I'm trying to indicate to you that all of this fancy duality, this state duality, Galois homology, and at the end of the day, it has something to do with TC. TC is some fancy version of THH. Already in THH, you can see a duality. And the way that we will observe the duality in TC is by checking that this simple duality at the level of THH is compatible with all the structure that exists on THH. That's circle actions and for the unit maps.
So the previous computation result, you allow p equal to 2 or not?
I think I'm allowing p equals to 2, yes.
Because previously you mentioned some Lagrangian result, which is p is no net. Like greater than 3, but now you don't.
Oh, I mean, so assuming and drivers were working at large primes because that's what they were able to do. But the results are going to be true at all times, even for this count.
Okay.
Just one more question. Ph, and the whole interpretation of L, will this also work for KO at T?
Yeah, so I want to sketch for you a very general reason for this statement here, where B is not just FP, ZP, or L, but where B could be a whole lot of rings, including KO at the prime too. So I want to explain why just this THH statement is something we can disprove for a large class of B.
In the general, do you also have a candidate for the class, for great relative class?
Yeah, I'm going to tell you now a very general story about why something like this is true for a large class of rings B.
Right.
See, maybe after I say that story, you can tell me what's unsatisfying about it. Okay, so what is the sort of situation that I think is analogous to the ring of integers in a p-added number field? I want to give some class of rings. And let's say we have an E3 ring. I think you could easily get away with less than E3, but just for simplicity, we can assume En3. And we'll say it's connective. Let's complete. Let's say pi 0 would be, let's say, local PI number field. The ring of integers. And, yeah, with number field. With residue field K. And this lowercase k here is just some finite field, which is the pi 0 of my ring mod the uniformizer. And then I'm going to say if the key conditions k perfect. So in the category of B modules, I want this residue field to be in the fixed subcategory generated by B itself. So examples. A itself satisfies this condition. So there's this ring of integers. So it's L. Why does L satisfy that? That's because if I take L and I mod out by B1 and then I mod out by P, I get FP. So I can get to FP from L in finitely many steps.
Pi 0 B to be.
Yeah, sorry. All right. K does not satisfy what's written here, but it's fine. It will turn out that the same argument works. I mean, really, I probably shouldn't have written it that way. Okay. Maybe K is so uninteresting that it works uniformly. Okay, also KO And so if I take KO and I mod out by eta, I get KU. And then I mod out by 2 in the bot element and I get F2. So again, I can get F2 by modding out a finite sequence of elements. Here I'm imagining that these are all P completed. U, EF, PTM, various instructions you can make with PPN tensor with some spherical width vectors. You know, a lot of things you can dream up that satisfy this condition if you want to. Anyway. What can we say about these P's? Well, first of all, let's note that we can form this tensor product, K tensor E with K. And what is this tensor product? This is a connected graded unit. So why, obviously be connected because we're taking a tensor product here, which has, for example, a torus spectral sequence that will show this is connected. It's graded because it's the homotypic groups or something. Connected in this strong sense that it's pi 0 is just K. And the key point here is that it's finite. And so why is it finite? It's because, well, first of all, K is a finite field, and it's built out of B in finitely many steps. So if I took K tensored over B with B, I would just get K. And so here I'm looking at something that's built out of K in finitely many steps. So it is itself finite. And it's a Hopf algebra because it has co-product, etc., coming from the fact that this is the kind of construction that always gives Hopf algebroids, but K is a field, and you get a Hopf algebra structure. So there's a classification of connected graded finite Hopf algebras. If you, for example, look in Margulis's book, there's an exposition of the fact that this implies interesting is a point graduality algebra. Okay. So just the fact that it's a connected graded finite Hopf algebra in fact implies that this thing has a dualizing class. You can see how this works in practice. For example, if B is the p-adic integers and K is Fp, this becomes just an exterior algebra on one class.
So sorry, just to make sure I'm following. So the K being a perfect B module is there precisely to like exclude something like the sphere, right? This sort of
It in particular excludes the sphere, but it's gonna play a large number of roles for us. But maybe the most basic is that this is a finite type of word.
Okay. And then the way you write it, it's like a little bit like an E3 ring with like where pi naught happens to be a ring of integers. Am I supposed to like think of whatever's coming really as an invariant of B, or more so of its like pi naught? Like how sensitive is it to?
Well, it's an invariant of B.
Okay.
I'm just trying to capture this property. I mean, the essential point is there's some kind of connectivity running through this story. But the essential point is that I want to be something like the ring of integers in the sense that K is a perfect B module. And that's in the remaining time, let me try to explain how to use that. So this whole Lagrangian statement is supposed to be something about PHH of B. So we can try to compute PHH of B, the coefficient in this bimodule K, the residue field. And this has some expression, right? It's the tensor B of. But if you just push symbols around and rearrange this, you can actually learn if this is another thing. This is the THH of K, the coefficients in the bimodule K tensor over B. Okay? It's just the formal manipulation of tensor products. And so here we have an expression where we're really working with the residue field somehow instead of some potentially complicated three ring, but now we have this interesting bimodule. Okay, now the Whitehead Kosnikov filtration. And this bimodule gives rise to a spectral sequence. It begins with the THH coefficients in pi star. And converges to pi star. THH efficiency. That's what we'll do here. Which again is just the same thing. This thing we're interested in. And now this thing is just A adjoining 0 by Boxted tensor with S bar of A tensor over B with K. So there's a spectral sequence converging to this. It starts with this finite Hopf algebra tensor, a polynomial ring on a degree 2 generator. And this object has the property that when I either invert or kill mu, I get a point radiality algebra. And furthermore, this is a Lagrangian. And so maybe let me just end the first day by saying that there are indeed lots of differentials that occur in the spectral sequence. But regardless of the pattern of differentials, the fact that the spectral sequence starts as a Lagrangian implies that it will end as a Lagrangian. This is a finite spectral sequence because this is a finite algebra, so its Kosnikov power is finitely many perfect pieces. All right, so next time we will talk about how to lift some of these arguments about THH to be compatible with things like nucleic filtrations, Frobenius, and circle elections.